So, yes. Ready, you can start.
Okay. Good afternoon, everyone. Today I will going to discuss about the autonomous driving based on the GNSS real-time kilometer position to to find the facility on the autonomous driving in the future. So I will talking about the theory about the technology, including the real-time kilometers and the network transport NTR/IP after and at that third look ahead distance. So after that, I will include about the autonomous driving testing and demonstration set up between in the slow speed and high speed autonomous driving between RTK GPS and the single GPS. Find which one GPS is better for the autonomous driving. So I will talk about the background of the technical theory. So in the RT, in the real-time kilometers position, the RTK is based on the GNSS signal. They use the at four satellite data to calculate your location. If the satellite is the number of the satellite more the uh, R1, RQ1 accuracy accuracy of the data of your location will be better than the 3 or 4 satellite. Also, it can reduce the double difference of the measurement and improve the position accuracy using the base and over data and reduce the code biases and atmosphere because the road choose reference station have more reference data to consider to the GNSS signal, so the RTK position can be more uh, accu accuracy accuracy for the position from the raw data. Then this the receiver can collect the data from the rover, antennas, position, and the other equipment. So this is the network transport of the RTCM Internet Protocol. Okay. The NTRIP is support to the RTK network. They can receive the data from the satellite and send the data to the internet and calculate the result. Also, the RTK position can will try reference station and extended Kalman filter analysis and handle the data through this technology. So I will discuss about the standard Kalman filter is a mathematical model that can determine the state of dynamic station. Sometimes the data will be unstable, so the Kalman filter can provide the optimized estimates in the noise environment. So also the single GPS are using the L1 frequency, but the RTK position are using the standard Kalman filter to position, so it will be more accuracy for the from the data. Also, it can use in the navigation, for example, in the SDK position for auto driving and analysis the test based on the data from the GNSS. So the main technology of the autonomous driving is the adaptive look ahead distance, because it can reduce the liable error based on the velocity speed. In the picture, the car is the point C. Adaptive look ahead point for the car to use the reference as a for the turning control. Also, the destination point can change from the D to D model adaptive. The car reduce the lateral error and enhance the control. So the adaptive must be included the error, lateral error. The LE is calculated with the raising point I plus 1 and the angle of the car current handling. So thing are the speed K times V, we can find the calculate the look ahead the distance. This is a video of about the autonomous driving in the car. About this. Okay. So the computer is also recalling the data from the sensor to the computer is calculated, then you send to the computer, send to the car system to control. So the background of the autonomous car navigation and control, the hardware should be used the laser and camera to connect and detect the raw data, and then transfer the data to the AI model to calculate it and decision to do the decision making. Also, they can use the adaptive look ahead distant data to for a reference to calculate it. But have a challenge with the GNS and RTK is the signal package and signal error. The tall building can be block the GNSS signal in the city. Also, the GNSS RTK lead to the base station for the stable communicated to correcting the GNSS data. So this is a setup about the demonstration of autonomous testing. They are using the 5-passenger car and the 1.6 gas line engine, and also the car can receive the 10 Hz signal, and the NTRIP can receive the one signal to the GNSS RTK. So I would discuss about the slow speed before I will talk about the equipment of connected data. They are using the car with the experienced driver, so we can excluding the human factor, so we can compare with the autonomous driving with the single GPS RTK GPS. So you can see the standard deviation about the RTK GPS and the single GPS. The picture A is a single GPS. You can see the standard deviation is larger than the picture B RTK GPS, around 68%. So that means the RTK GPS is more accuracy than the single GPS position. So this is the picture compare on the satellite map. The right hand side, you can see the straight line. The single GPS will some offset in the straight line, but the RTK don't have any offset. They are always stable in the straight line. But also you can see the single GPS always offset in when the car turn around to the other road. So you can see the RTK is more accuracy and more standard in this testing. So in the slow speed autonomous driving, they are using the 6 km per hour to starting in the open area. You can see the size and the GNSS, RTK, and the single GPS are used mark the waiting point between 2 meters. So you can see the single RTK are more unstable between lab. So you can see the point Q, the single GPS fail to finish the testing. They are stopped in QA because it's based on the safety reason and the single GPS was unstable. Instead, the RTK GPS will complete a full lap and no serious error on each waypoint. So you can see the picture B, the single GPS, the turning angle is larger and fluctuation, and it also is a high frequency transition to control the car to turn left and right. Instead, the RTK is a more angle and more stable than the single GPS. So the RTK GPS is better in the slow speed automation in this case. So I will talk about the high speed autonomous driving. So they have two chain A and B to testing the high speed auto driving. Also, they need to finish the single lap, and each lap have 10 corners. So this is the basic data of the auto driving vs the human driving information. And the mode information are similar. So this is the testing result. You can see the GPS position, the turn left or turn right angle are always larger than the RTK GPS, but the mean of the RTK GPS and the single GPS are always similar. The one is 102, the GPS is 111, but the standard deviation, the RTK is smaller than the GPS. That means the RTK is more stable and will less error between the driving. Or instead, you can see the GPS position have larger standard deviation. So that means the driving will not unstable, will have more error, it will have some potential accident between driving. So that can have 3 factors. In fact, the speed of the autonomous driving. So in the point T or the point T4 is a starting point. If the turning angle LE is lower, the cars will less damage and more stable. If the LE have higher, it will increase the potential accident and unstable. The T4 is sharper for turning waypoint and lower, and it is a lower target speed. So also in the T6 is have the large LE because it is have a higher slope, carry more engine power to control in the waypoint T6. So in the graph B, it have the high speed is a starting point and the slower speed at the T4. Also, it will reach 5 kilometers due to the limit acceleration performance. In the graph B, the speed and time are similar to human driving, but the time is slower than the RTK over 30 seconds. So you can see the RTK GPS success when done in the high speed autonomous driving. So it can more accuracy with the human driving. The error will be below the 0.1 meters. So in the conclusion, the low cost RTK will have a higher accuracy for position. Also, the accuracy is more than the 20 time. RTK is better than the single GPS, but also it show the auto driving have a potential development in the future. This is a reference list. Thank you. This is the end of my presentation. Thank you.
Okay, you spent around like 80 minutes, so it means we only have 2 minutes for a QA session. So generally I think this is I mean it's a good presentation with lots of contents, including the like from single pole positioning to the RTK, and also you introduce a paper is related to the high speed self-driving cars. Okay, high speed self-driving cars. So this work is done by the team from Korea.
Yes.
Okay, I see. So which year is like
To around 20 and 21.
2021? Okay, it's quite new paper. So I think you have very good foundation in terms of the results, especially like from the major principles and the results. For example, you mentioned quite a few times that like in this kind of scenario, because you are talking about the high speed driving. So I can see from the scenario, I mean, it's quite open chaos, it's quite open areas. So that's why you can achieve like 0.1 meters of accuracy. So I have several quick comments. So yeah, still I think the slides, I mean the content is good. So sometimes I can find the style of the slides slightly inconsistent. For example, in some of the page the font is Times Roman, and sometimes of the page slides the fonts. I mean the fonts is Arial. So you can try to make it more consistent if possible. So the second comment is but still you should get rid of the scripts. Yeah, just because it's hard, because like just 2 weeks you need to fully get familiar with the paper is quite difficult. But still, if you can try to get rid of the scripts, and yeah, also some of the words. Okay, you have some like some it's a challenge for you is some of the words you are not familiar with. For example, like autonomous. Okay, let's see autonomous. The words you can practice more, make perfect, right? So okay, so that's all my quick comments because time's up. Okay, so thank you again for your next presentation. So the next one is Emily. Yeah. Okay, so let me record the time. So Emily, the same. You get 15 minutes for presentation and 5 minutes for QA. So if you're ready, I will record time. Okay, thank you.
So, hello everyone. Today I will present you my paper, which was entitled LiDAR Inertial Odometry Aided Robust LiDAR Localization System in Changing City Scenes. So my presentation will be separated in those different parts. So let's start right away with the background. So transportation of people and goods in the last 100 years has changed at a drastic pace, and that's whole technological concepts such as autonomous delivery and driving begin to appear. And one of the primary requirements of an autonomous system is a defined map area. And in order to navigate autonomously, the prevalent approach requires precise localization. But it's difficult to implement, especially in a dynamical, changing environment. So, as an example, here you have a map with and the different color represents how likely an area have a change in his environment. And there you have a zoom on one of this area. And effectively, you have the difference between the two pictures. There have been metal wall that have been removed, and that's what we can see in the previous slide. Now the suggested solutions. What has been proposed in the article is to integrate LiDAR inertial odometry together with a matching-based global LiDAR localization module. And both of the measurements are used to give an optimization framework. So the premise are the framework for vehicle localization, a LiDAR inertial odometry that tightly couples LiDAR and inertial measurement and incorporates both the occupancy and LiDAR intensity cues, and finally, a robust vehicle localization system. So there have been related work. So firstly for the long-term navigation, but the thing is, like, the solutions that have been proposed for the long-term navigation are focusing on two specific problems. So that's why the paper was proposing to add LiDAR inertial odometry to make a more global solution. So it will allow us to provide clear estimation and compensate the motion distortion and tighter local motion constraints. And all of this we are going to use to give the solution. So here you have the architecture of the suggested solution. There is four principal modules. The LiDAR inertial odometry, the post-graph fusion, the LiDAR global matching, and the environment change detect. The LiDAR global matching is a localization method that match online LiDAR scan against a prebuilt map and conducts a three-dimensional estimation. So X, Y, and the yaw. And the other two dimension can be estimated by reading as you can see, reading measurement. And the other two modules, so LiDAR inertial odometry and post-graph fusion, are formulated in terms of solving different maximum a posteriori probability estimation problems that I will explain in the next slide. So firstly, let's talk about the LiDAR inertial odometry. So as you know, the LIDAR inertial odometry plays an essential role in our system, in the system, in promoting localization performance in challenging circumstances. It will estimate relative pauses between frame and simultaneously help us build a local map called map. But here we are adding 4 extensions. So the first extension is to add the method of the 3D occupancy grid instead of the 2D one. And it will allow us to applicate it in a 3-dimension environment. Then the next one is to incorporate inertial cues to provide motion prediction and relative constraints between frames. And the third one is to, in consideration of the rich information from lane or road surface markers in the different scenario, we are going to incorporate LIDAR intensity cues during the occupancy registration, and it will provide valuable texture information of the environment. And the final one is to apply a coarse-to-fine manner while solving the non-linear optimization problem by introducing multi-resolution into our occupancy grid implementation. So let's talk a bit about the map estimation problem. It's common modeling. So that's what we are going to use in the method. So first, the density estimation, the common modeling problem involves how to estimate a joint probability distribution for a data set. So for a given data set, we have to find the function, the distribution, and the parameter, but it's too challenging, and that's here we are going to use the map estimation problem. So it's an approach frame. The approach frames the problem as optimization and involves searching for a distribution and set of parameters for the distribution that best describes the observed data, and it's used the Bayes theorem, but we are going to simplify it because we want to optimize the equation and not to resolve it. So that's why we are going to remove the denominator because it didn't depend of the numerator from what I understand. And so in our situation, if we have X, the data set, and theta, the parameter from the distribution, we have this equation. And in order to solve the optimization problem, we have to find the maximum of the given equation you have here. So in all the terms, with all the terms, it gives us this difficult equation, but it's basically the same thing as I showed you in the last slide. So, but with xkl is a state with tk is the position, and rk is like exponential of omega k, and omega k is the orientation. It's a bit difficult, but and then zk are the point cloud inertial measurements respectively. And so firstly, if we make the assumption of zero mean Gaussian-like probability, the So the second part could be defined as this. Yes, and the second part, yes, and the second part could be defined as this one. I will not read it, but it's quite huge. With different terms like the variance, which is used to weight the probability term in the optimization at different resolution of the SUMAP, and etc. And so SSOEP is the sum of squared occupancy probability, and SSID is the sum of squared intensity difference. And same here, all the terms are explained as you can see. So, but now we want to use, as I say, what the LIDAR inertial odometry give us. It will give us good relative constraints in the frame. And what the LGM module will give us, it will give us global constraint. Finally, it will give us a post-graph-based fusion framework in order to have a good global localization system. So here is what we call a Bayes framework, as I remember. So basically, it's all the item represents the variables of all the system, and the link between them tell us if the different variables are conditionally dependent or independent. So if there is link, the two variables are conditionally dependent. So it will give us, it will allow us to formulate this fusion problem as a map estimation, as I presented you in the last slide. Again, a big equation, but we can develop it like this with RKSO, RKI, and RKJ, which are the odometry, inertial, and global residual, respectively. So first, for RKJ, it's a bit high. It's the global residual cost. It is defined as this, just here, where the big RG could be defined with the big matricial equation. And we have the covariance, which can be also defined here. And we have the other term, etc. So now for the environment change detection. So the submaps generated in the LIDAR inertial odometry module allow us to estimate the relative pause between frames, but also to detect the environmental change. Why? Because we are going to project our 3D multi-resolution submap onto a ground plane. Then a 2D submap in the same representation format to our pre-built localization is obtained. And we are going to compare cell to cell with the submap and the map, and it will allow us to see the detect. It will allow us to see the environmental change. We can also quantify this with those different variables which allow us to evaluate how likely the environmental change exists in the cell. So with all the different variables, such as the intensity mean or variance, or the altitude mean of the submap and the pre-built map. And we will formulate the occurrence of the change within each cell as a binary state estimation problem addressed by the binary Bayesian filter, which is a type of probabilistic model used to estimate the likelihood of a binary event or state. It applies again to use the Bayes theorem. And so the model we are going to use to update this model is just here with so with the binary state variable that denotes the occurrence of the change within the cell. Voila. And we can define all the measurement, as you can see here. It's again a big equation. But now let's talk about experiments. For the context, the paper used two different data sets. One in San Francisco Bay, where the car has been drive on a distance of 380.5 kilometers, and another data set, which is the internet data set in Beijing, China. But this one, we want one with map error on environmental change, such as road construction, closed lane, dense traffic, and so on. So let's first the result of the Apollo Source Bay dataset, the one from San Francisco. So how to read this? We have to look for the lower maximum horizontal errors. That the lower it is, it will demonstrate that the proposed design smooths the trajectory and make our system reliable in extreme circumstances. It's the same for their international dataset. We have here 3 different dimensions. And again, we have to look for the errors, but maybe we can better understand with visual results. So here in different situations, we have like, so for the first this situation, it has the experiment has been made at a place with long-term seasonal change. The third one is the same one as the beginning. It's where the metal walls were removed and crossholds are repent. And the next one is new walls were built, and the last one is a place with dynamic objects such as many heavy truck on a narrow road. And how to read this? So here there is not 2 cars but 3 cars. The red one is the green one is the system. The green one, the red one is the one with only the LiDAR global matching without the LiDAR inertial odometry module, and the blue one is the ground truth. What is interesting is that the blue car is hid by the green car, and it shows us like the system actually works. Finally, there is some ablation experiments that had been made to show how how great is the performance of the system. So we they conduct an experiment where with only the LIO module, and they obtained a translation error of 0.93% and a rotation error of 0.0057 degrees per meters. And there is also another experiment with different intensity cues. And again, we can see like the accuracy is still quite good, but the best one is with our intensity and intensity Q and multi-resolution. So to conclude this big presentation, we have presented a robust, the paper have presented a robust data localization framework. Designed for autonomous driving application, and especially contouring the localization challenge in changing citizen. And so it includes LiDAR inertial odometry. It aids the LiDAR inertial odometry module will aid the localization system in the prevention of localization. And it also proposes an environmental change detection method. And all this make the system attractive to real commercial deployment. Thank you.
Okay, so yeah, it's around 20 minutes. Okay, at least I will ask some quick questions. So generally, I think Emily, this is a very good presentation with very solid content. So I can see your efforts. You make a lot of efforts to at least you input all those equations, right? Especially from Bayesian theory to the factorial optimization and formulate all those stuffs. Can we go back to the page 1? Let's quickly go through the slide from page 1. Yes, I think okay, this is good. So first page. So this is Hong Kong. I mean, okay, I see. Okay, next page. Okay, I mean, where you get this figure? This is from ChatGPT. I mean, the background.
Good page. And this is
I mean, the first page. I mean, the first page. This one.
it's like a that I duplicate to make.
Okay. So the background image is from Google. Oh, I just thinking about your design. So next page. Okay, so that's clear. Yeah, that's wrong because this outline, this plan is more like the outline of the papers, right? Yes, next page. Yeah. It's good. So this is South Bay of San Francisco. Yeah, next page. So yeah, it's good. I mean, you discuss the problem first. The problem is the changing environments and how to do localization and detect the change of the environments. Okay, next page. Yeah, it's good. Clearly see the problem. Okay, change. For example, previously there's no boundary, so currently we get the boundaries. Yeah, next page. Yes, we're quite clear. Yes. Go ahead. Yeah, and also, yeah, it's good. Yeah, can you just go back to the experiment parts, I think. Yeah, experiments. For the methodology part, I think it's quite difficult to clearly explain. Yeah. So can you go back to the experiment? You have a table. Next page.
The big one.
Yes, I think, for example, just this page. If you look into the 1, 2, 3, 4, 5, the fifth columns, okay? For example, the Sunnyvale big loop. So see, for example, using all solution, the errors, the percentage of errors like below 0.1 meters is around like 78.72%. This company is quite honest. It means at this moment, they have around like 30%, 20% of the results with an error of more than 10 centimeters, right? It's still large. I mean, at least it means at least from this table you can see we still have some rooms to improve the accuracy. We still can see some errors is more than 10 centimeters. Yeah, can you go back to the last page about conclusions? Yes, they have no future works.
But I remove because my presentation was already big.
Okay, so thank you again for a nice presentation. Okay, so last one for today is Suhat. Okay.
It's great.
Yes, of course. I need to open the screen as well. Oh, this is a conference?
Yeah.
You're also right?
Yeah.
Wow. How many pages? 88. Okay, that's great. So if you are ready, I will record time for you. So, okay, we start. Yeah.
All right.
So everyone,
I'm a student, and I will be presenting a paper titled System-Driven Prediction of Orbital Parameters for LEO, which was presented earlier in Genesis Plus 2024. So, PNP from LEO, low Earth orbit satellites, has become a popular topic, a recent trend, and the PNP among the PNP researchers because of advantages that LEO provides us. So there are several constellations that we have. We have Starlink, we have Outcom, we have OneWeb, we have Iridium. Mostly, they're for communication purposes. So as I was talking about the advantages, LEO gives us higher signal strength as the satellites are almost 20 times closer to Earth than the GNSS satellites. So we get a signal power of 24 to 34 dB higher than the GNSS signals. We get enhanced security as these satellites operate in a wider range of frequencies. So the signals are less susceptible to interference, and LEO also has the potential to minimize multiband issue. So as the satellites are closer to Earth, they need to orbit the Earth much faster than the GNSS satellites. So the orbital time is around 190 to 120 minutes, and this gives us a rapid change in geometry of the satellite, which can potentially solve the problem of multiband. So with all these advantages, LEO satellites can augment GNSS with superior performance and operational resilience. But unlike GNSS satellites, LEO satellites do not share their ephemeris data because they're operated by commercial companies, and they're not really made for positioning purposes. Then how do we do positioning? Because we need the satellite position and velocity to estimate our position. In order to do so, the most popular way to get the satellite position and velocity is to use the TLE dataset or the two-line element dataset. So the two-line element dataset contains the orbital information of a satellite that we can use as our input parameters for dynamic models like STP4 that can give us the satellite position and velocity for a certain epoch, which we can use for our positioning application. But the problem with TLEs is their infrequent update rate, which is 1.7 TLEs per day. And this infrequent rate can lead to errors in orbit propagation, which can affect our positioning performance. Yeah, that is a challenge to the application that rely on high orbital data. So if the satellite's estimated position is deviated from the true line of sight, which is excess here, it can cause a positioning error of 1.5 kilometers, which is huge if we compare it to what we can achieve today with our latest GNSS technologies, which is less than 10 meters of mean square in challenging environments. So to solve this problem, there have been numerous studies to correct the error or model the error. Some people introduce new dynamic models. Some people use deep learning to model the error, and some people use satellite laser ranging techniques to obtain the satellite position and velocity directly. So a recent study, a recent work, a significant work that has been done by Dr. Kusasti was to use the TDNN or time delay neural network based orbit prediction framework that uses the satellite position coded from the received signal for training data. But there's a problem with this approach. That is that this is not feasible for all the satellites because LEO satellites we don't know the signal structure. So it is not feasible to decode all of their signals and then obtain the satellite position and velocity. And the training data is also small. The training data that they used was like 600 to 700 data. So what we are proposing here is to use historical data, theory data, or training that gives us more feasibility and applicability for LEO satellites. So why are we using TLE? And TLEs are basically they're widely available and accessible. That makes them convenient and consistent source of publicly available data. TLEs have extensive historical record, so that is useful for training recurrent neural networks or feed-forward neural networks. And TLEs also reduce the dependency on real-time satellite tracking systems. So the proposed algorithm uses LSTM, which is a popular network used in time series prediction problems. So I will not be going through the detailed architecture of the network. You can refer to the paper here if you're interested. Rather, I talk about the vanishing gradient problem. So the vanishing gradient problem is a significant challenge in training deep neural network. So the problem arises when the gradient that is used to update the network's weights become exceedingly small as it propagates back through the network. So LSTM solves this problem by introducing its gating mechanism, especially the forget gate. So forget gate decides what information it will let pass through and what information will be discarded. So by selectively discarding irrelevant information, forget gate maintains a stable gradient, solving the problem of solving this problem. So for the proposed algorithm, we use historical GAD. We use them as our parameter. We feed them into the network. We optimize the network hyperparameters by Bayesian optimization. We get the predicted orbital parameter, which is a fairly simple idea. But then how is it different? Well, it is different because we are proposing a sequential prediction algorithm here. So the sequential prediction algorithm has 6 different LSTM models for 6 orbital parameters. Each of the models gives us a predicted value for a specific orbital parameter that is used in the later models as a test feature. So the sequence here is crucial to obtain all the required test features, and we will be discussing later with why we have chosen this specific sequence. So each of the models has 3 stages: pre-processing, hyperparameter tuning, training, and prediction. So in the pre-processing stage, we obviously need to process the raw data to make it usable for our training purpose. We optimize the hyperparameters using Bayesian optimization, and finally we train our model and predict the parameters for specific epoch. So as for the pre-processing state, as you can see from the 2 figures here, one is for argument of parity and another is for mean anomaly. So they have huge outliers in their historical data set, which is not suitable for training deep neural networks. So we need to remove them. So in order to remove them, we have set a range of acceptable values in the network. And for other pre-processing steps, we have taken the sign value of RAN and inclination. They both are angles. So we have also included Earth to Sun distance and Earth to Moon distance. We have included these 2 features because they're relevant, and these 2 features vary periodically, which helps our model to learn complex relationship between different parameters easily and efficiently. For semi-major axis and SU anomaly, as they cannot be directly found from the theory dataset, we need to use the basic orbital mechanics equation to obtain it or to calculate it from the existing theory dataset. And for normalization, we have used V-max normalization because the different parameters are in different scales in the theory dataset. For hyperparameters, we can see the search space here from the table. We have used the Bayesian search technique, which is algorithm that dynamically models the objective function, so that the optimum of the function can be found in the quickest time through a series of evaluation. We have also used early stopping in order to avoid overfitting, and we have also used a feature that increases the learning rate depending on the validation cost. For training and prediction part, you can see from the table that each of the model for each parameter, they have a unique combination of training data set. So these combinations are not arbitrary. We have reason behind why we have used this specific combination, and we will be discussing later why we have chosen these combinations. But let's focus on eccentricity. So for eccentricity, as you can see, that the model for eccentricity uses semi-major axis as one of its training data, training feature. So in order to predict a value for eccentricity, we need to have a test feature or a semi-major axis data for that specific epoch as well. But we cannot obtain that without a predicted mean motion value for that specific epoch. So that is why the sequence here is important, and we need to maintain the sequence in order to obtain all the required test training features for the model. For the training and prediction part, the first 2 models are mean motion and inclination. As you can see from the mean motion, As you can see from the mean motion historical data set, it has very low variance in its historical data, which indicates that it is a fairly simple and stable parameter to predict. So because we have limited data available at the moment of training our first model, we only have the access to epoch and the distance from sun to earth and moon to earth. So we can train the model for mean motion and inclination first, because they are stable and they have very low variance. In order to obtain a semi-major axis data or a test semi-major axis data for the later model, for eccentricity, we need to have a predicted mean motion first. For the later model, we have eccentricity and RIM. Eccentricity also has a low variance, but we need to have a semi-major axis predicted or calculated semi-major axis from a predicted mean motion first. That is why eccentricity is in the third place. And eccentricity and semi-major axis, although they are not related directly, but they both define the shape of the orbit. So they both are relevant to each other somehow. And also, if we include semi-major axis, it gives the model one more parameter to train on and predict on. And for RAN, for this one, you can observe that there are some discontinuities here, which is not suitable for our model. So we have solved this problem partially by reducing the training data set. And that is why we have kept the model for this parameter in the fourth place, after we have three predicted parameters first, so that we can include them in the training data set for this parameter, so that it somehow has a sufficient amount of data for training. For the other two models, argument of Fibonacci is not used for training any other models. So the sequence for this parameter is not that important. And for mean anomaly, it is important that we construct the orbital plane first. So we have calculated predicted all the orbital parameters first, and then we have kept the model for mean anomaly so that we can rely on the other parameters to produce acceptable prediction. So for experimental setup, we have trained the model on Starlink of the historical data of Starlink 1007, as we have observed large time gaps in the historical data. We have used 2160 sets of daily data set, which might not be sufficient for a deep neural network, but this is what we can find for Starlink, because they're comparatively new satellites. And we have also done 50 trials for each of the elements, and we have reported the mean value for further experiments. For experimental results, we have the predicted values for mean motion, eccentricity, and inclination on this sheet. So we have predicted for the most recent TDC epoch. So we have compared our predicted results with the most recent TDC orbital parameters here. And you can see from the three blocks here that the predicted values do not deviate much from the central value, which indicates that the models are stable and giving us fairly acceptable prediction. So as you can see from the table here, the difference is very low. So these values are acceptable for further experiment. For the model for RAN, as we have already said that we have reduced the training data set for this parameter because there were some discontinuities in between. So that is the reason that we have some large deviation from the central value here in the plot. But we were able to predict an acceptable value for this parameter as well, as you can see from the table here. For the last two parameters, mean anomaly and argument of Fibonacci, we were not able to predict acceptable value. This is due to the fact that mean anomaly and argument of Fibonacci, they both depend on the perigee of an ellipse. So for LEO satellite, the orbit is nearly it's a near circular orbit. So in a near circular orbit, there is basically no perigee. So these two parameters are not well defined, and it is difficult for a machine learning model to learn their nature and to to find the relationship with other parameters. So we were not able to predict acceptable values for these two parameters. So for further experiment, we have used the real values from the most recent theory that we have for the dynamic. For further experiment, we have propagated the position and velocity for next 3600 seconds or 1 hour with the predicted parameters, and also we have outdated theory as well. And we have this is the RMSE plot for both position and velocity. So the RMSE is consistently lower with the predicted data, as you can see from the blue line here. This indicates that the estimated position and velocity can be useful for positioning application. So to conclude, we have proposed a novel RNN-based algorithm using LSTM to predict orbital parameters for a specific epoch for LEO satellites. We have addressed the limitations of traditional models to handle outdated theories. We have still predicted 4 out of 6 orbital parameters, and we have improved the position and velocity estimate for the proposed technique that can be used in any application once all 6 parameters are predicted with high precision. So for future works, we are planning to add some physics-related constraints by customizing the loss function of the neural network. And we are also we will be focusing on pre-processing and data pre-processing stage, and we will be implementing data segmentation and smoothing techniques and see if we can gain some better results. That is all from me today. Thank you for listening, and we are now open for questions.
Okay, so very nice talk. Yeah, professional talk. So I guess several questions in terms of the. So can you go back to the experiment results? Yeah, I will not go through all the slides. I think generally the slide is quite good already. So can you go to the results? So you have one result. It's a prediction of the. I mean, the y-axis is the kilometers. The RMSE differences. Next page.
Okay.
Yeah, very last page. Maybe a very last 3 pages. So I mean, from the upper left, so this figure means the error of the orbital. So the RMSE is the orbital. For example, the trajectory errors.
This is the position for the positioning results.
So this is the position error, or this is the
This is the position
position of satellite. So it means the okay. So the upper part, the difference is around like 1, 2, 3, 4, 5, 6. The difference is around like 6 kilometers, right? Oh, yeah.
This is actually not enough for
Yes.
but we have made some improvements.
So okay, one more question. So actually, I mean, because the Starlink, they will not, I mean, broadcast the precise infamous data, especially for the position of the satellite, right? So I think yeah, it takes some time. So next question. So when you train the networks, I mean, especially train INN with STM, so you only use the data set from Starlinks, right?
We only for Starlink.
Or you also use some other data sets?
Experiment with
Iridia.
Yeah.
Iridia, yeah.
We have not included in this paper.
Oh, I see. Yeah, maybe you can extend this with, I mean, generalize with more data set to, I mean, in your journal version.
Yeah.
For
Starlink, we don't really need this algorithm because Starlink publishes the data. Precise data to 10 meter accuracy.
And 10 meters is still too big.
I mean, the position.
Oh, I see. Okay.
But we use Starlink because the time gap between each theory was huge. It was sometimes more than 24 hours.
Yes, I see. Yeah, generous is a really good slide. So you already present. Have you also get the award? For example, we have some base presentation award in the ION. So who gets the base presentation award in your session? Which team?
Yeah.
Oh, Warsaw. So it's about what? About, I mean, what's the topic about?
I think he will be chairing the session with you next year. She will be co-chairing the session.
No, I'm talking about what is the topic about? I mean,
Learning.
About machine learning. Yeah. Machine learning plus navigation.
Machine learning. in determination.
Ah, interesting. Okay, I see. Okay, so thank you again for your nice talk. Okay, so I think that's all for today's group presentation. So see you next week. See you next week. So the error is still like around like several hundred kilometers for orbit parameters. Oh, okay. Okay, still
Yeah,
go. Okay, that's all.